Hello, everybody, and welcome to the Homi Bhabha lecture webinar. I think the numbers have been stable for a little bit now, though I'm expecting people will join during this introduction. So don't worry if you've missed a little bit. Just to point out some of the features of today's talk to begin with, there is a Q&A button at the bottom of the Zoom window. If you have a question for our esteemed speaker, then please do type it into that box, and we will do our best to get through as many, if not all, of the questions at the end of the session as we possibly can. I will be reading those out. And please, if I could ask you to stay unmuted, and we won't interject with the speaker, but rather save all of our questions until the end. And we do have an ample 20 minutes to go through all of the questions and answers that might come up during this talk. So please hold your fire until then. So the Homi, Bhabha and Cockcroft-Wharton lecture series is a bilateral exchange of lectures between the Institute of Physics and the Indian Physical Society Association, the IOP and the IOP and the IPA have been running this lecture series very successfully since 1998, and we always focus on topics that are global challenges, the global challenges in which physics plays a major role. And today's lecture is no different, shedding light on dark matter in the universe. So today we will discuss one of the next great mysteries to unravel, dark matter. We will explore the observations that compel us as scientists to believe that it does exist, and how this dark matter signals could connect to our accepted theories of particle physics. We'll hear about ways in which the experiments aim to probe the nature and properties of dark matter, and we'll look in particular at this at the LHC, or the Large Hadron Collider. It was my great pleasure to introduce our speaker today, Professor Rohini Godbole, a theoretical particle physicist and currently honorary professor at the Institute of Science in India, Bangalore, who will be delivering today's lecture. Professor Godbole retired from the Center of High Energy Physics at the ILSC after 25 years as professor. She was earlier at Mumbai University, the Tata Institute of Fundamental Research, and has worked in a number of universities across India, Europe, the USA, including at CERN and Geneva. Her research over the past 4 decades is far too great to go into here. We only have 5 minutes for this introduction. But just to tell you a little bit about her, her work exploring the standard model of particle physics, and indeed beyond the standard model of particle physics, has resulted in over 300 peer-reviewed journal publications and a graduate textbook. Her pioneering work on probing hadronic interactions of photons have provided important insights to the design of electron-positron colliders, and have helped to probe the standard model and beyond standard model physics at experiments and many colliders. A fellow of the World Academy of Science, she has been elected to 3 Science Academies of India and serves as the Vice President of the Indian National Science Academy. She also is and has been a member of different national and international advisory bodies, including the CERN India Task Force, which is now a member of the steering committee. She is also chief editor of the Pramana Journal of Physics and the IOP Physics Journal G. Professor Godbole has also been an avid supporter of the cause of women in science. In this capacity, she is co-editor of the book Lilivati's Daughter, The Women Scientists of India, which is an autobiographical look at various sketches of female Indian scientists. And she chaired the Committee on Equality and Inclusion for India's Science, Technology and Innovation Policy in 2020. Amongst these many achievements, one cannot miss out some of the awards and accolades that Rohini has received in recent years, including contributions to science and society recognized by the Padma Shri, conferment of the Padma Shri in 2019, the Karnataka Academy Lifetime Achievement Award in 2021, and the French Honor Ordre National du Mérite in 2021 also. So without further ado, let me stop talking and hand you over to Professor Rohini.
So thank you very much for this very, how should I say, laudatory introduction. But friends do this, so thank you again. I am really very pleased to be giving this talk, and I would like to thank the organizers of this series of lectures for inviting me to give this very prestigious series. It's good and bad. It's online, so I don't have to travel, but it's bad because it means that I don't get to meet my friends in the UK. So today, as has been told to you, this is the first of the Homi Bhabha lecture series, and this is a common IPA IOP lecture. And even though my announced title was Shedding Light on DM in the Universe, because of my own expertise, what I have done is that I have put in the bracket at the LHC, which is at the Large Hadron Collider. But I would, in fact, as was said very clearly, touch upon very many different aspects of the dark matter. So the plan of my talk is that I would first tell you what are the current frontiers of exploration in high energy physics. And as has been already told to you, dark matter stands at the top. And then I would kind of tell you what are the questions that the existence of the dark matter asks us. Then to answer these questions, first we have to hunt for the evidence for dark matter in other places other than the one where we have seen it. And how can we do this at the Large Hadron Collider to understand the mysteries of the dark matter? Will it help us or will it not be able to do much? So the current status of elementary particle physics, the accepted worldview is, and this is something that has happened over the past 100 years, I would say. I mean, more than that, since the time Rutherford found the nucleus, we have come a long, long way indeed. And now we know that the fundamental particles, the elementary particles of which everything is made up of, are the quarks and the leptons. And they interact with each other through force carriers, which are bosons, which are spin 1 or spin 0. The spin 1 are the force carriers, the photon, the WZ boson, and the gluons, carriers of the electromagnetic, weak, and strong interactions respectively, and the omnipresent Higgs boson, about which all we have been hearing for the last 10 years. Now, if this was, you could have asked the question why this should be of interest to people other than the 10,000 particle physicists the world over. The very simple reason for that is that the laws of particle physics, which we have found to be functioning at distant scales of Fermis and smaller, seem to be of relevance in addressing things that happen on cosmological time scale, happened actually, like the beginning of the universe, and happen at the astronomical distance scales like megaparsecs or even bigger than that. And 1 parsec is, just to give you a sense, is about 3.27 light years. That is the distance that light travels in 3.27 years. And just to again set the scale, light from sun takes 8 minutes to reach us, and we all know how far sun is. Now, the point is that the laws of particle physics, which we have been investigating beginning from Rutherford, at the center of the atom, at the center of the nucleus, and even more shorter distance scales, these seem to be relevant and providing some important input to gain an understanding of things such as how was everything formed, how were the protons and neutrons and helium and hydrogen, how were they formed in this universe at all, and can we explain the relative abundance of different elements in the universe? Do we understand how the stars and galaxies were formed from the first Big Bang? Now, these questions, answering these questions, requires a lot of knowledge of cosmology, astrophysics, but it requires very essential inputs from the standard model of particle physics, and that is why the laws of particle physics that govern the interactions and this particular understanding that we have got and which was confirmed at the Large Hadron Collider completely 10 years ago almost, this has relevance to many different things, and therefore it is of interest not just to the 10,000 particle physicists, but it is of interest to all of us who want to understand the secrets of universe, the secrets of nature. Particle physics actually finds itself in an extremely peculiar place. And since this is a talk in the UK, I can kind of, when I talk of a book, people might actually recognize it. So if I steal from a book, A Tale of Two Cities, with full apologies to Charles Dickens, the first line in that book was, "It was the best of the times and it was the worst of the times." I think we can say the same thing for particle physics today. It is the best of the times and it is the worst of the times. Now, why is it the best of the times? Oh, 10 years ago, we found a particle, the standard model Higgs boson, which proved that the theories of our particle interactions were completely correct. We had understood it perfectly. But we don't have the glimmer of particles or interactions beyond the standard model, what we by and large call BSM, and I will use that word time and again, that was promised because of the observed properties of the Higgs boson. Theory had kind of said that if the Higgs boson has these properties, we have very good reason to believe that there should be particles or interactions beyond the standard model, and we still haven't found any of them. So it is the best of the time, that is the blue, and it is the worst of the time because of these things written in red. So that is the situation. People may not be particle physicists here, but all of us understand some physics, and therefore we know that Lagrangian is a kind of a language in which we write equations of motions, and I can derive equations of motions of a system starting from a Lagrangian. So this Lagrangian, which fits on the back of a t-shirt or a jacket which you can buy in the CERN curio shop, this actually describes more or less, with more exact statements, but more or less this pictures the Lagrangian for all describing equations of motions of all these particles. So if we have been able to do this over the last 100 years, is the journey inside the heart of the matter now over? And the answer is actually no. Now, you might say that is it only because these particle physicists, they have been in good job for last 100 years and they want to keep themselves occupied. Is that the only reason? Actually not. There are a large number of cosmological observations there are a few things, as Horatio will say, in the universe, which we still have not understood, or we have an incomplete understanding in the framework of the standard model. And these different puzzles are of relevance for particle physics because particle physics has cosmic implications, as I already told you. And Bethe or Gamow or Steven Weinberg, who recently passed away, were maybe three giants who I can imagine who pioneered this cosmic connection of nuclear and particle physics. And that is the journey and that is the path on which now most of us particle physics community of a certain group of it seems to be following. There are many pragmatic reasons to believe in that there should be physics beyond standard model, and that is the BSM physics. Now, out of these, three are cosmic reasons. One is, which has been in the title of this talk, that there exists a lot of matter in the universe that does not shine, and that is very poetically called dark matter in the universe. The existence of this dark matter, this did get a Nobel Prize in 2019. Then there is matter and antimatter asymmetry in the universe. Even though at the beginning of the universe there was equal amount of matter and antimatter, in today's universe we have complete dominance of matter over antimatter. That I would call baryon asymmetry in the universe, BAU. Third is universe seems to be accelerating and not just expanding, and this has given rise to an idea of dark energy. That's also a cosmic puzzle. And physicists finally wants to understand, write down theories which would then explain observed experimental facts which do not fit into the picture that we have developed so far, and that's how science progresses. So from a point of view of a physicist who wants to understand the truth of the laws of nature, these three observations must be somehow explained, and we must achieve a theoretical understanding of these three puzzles. From a perspective of a particle physicist, apart from these three big observational puzzles, there are actually some more reasons which I won't discuss in detail. Perhaps if we had the question and answer, we might have some reason to touch upon them. But one is what we call that to cure this is a very theoretical and esoteric thing, that how to keep the Higgs boson light. Nobel Prize of 2013 went for the discovery of the Higgs boson, which determined its mass, and its mass is about 125 GeV per c square, which is about very close to the mass of a Z boson or a W boson or top quark, more or less of the same order of magnitude, and that's what we mean by saying that the Higgs boson is light. And theoretically, this is a puzzle, how the Higgs boson is light. So that's one puzzle. Then the non-zero mass of the neutrinos, which got the Nobel Prize in 2015. We don't understand how theoretically. We theoretically also do not have a basic understanding of the huge hierarchy in the fermion masses. Then we want to always, unification of couplings was a dream which even Einstein had. So do they, all the three couplings, do they ever become one and the same? And can we ever include gravity in this description? And now with the latest, one of the latest Nobel Prizes going to the discovery of two of them actually, gravitational waves and black holes, the need of trying to find a quantum field theoretical description of gravity and building it all together in one picture is sort of now stronger than ever before. So as you can see, there are many reasons, but I have listed the first one, which is the dark matter in the universe, and that is like the most biggest observational puzzle that we have right now. Now what is this? I will go much more detail in the next few slides, that the contents of our periodic table of particle physics, I call this first list that I gave you on my first slide of quarks, leptons, etc., I call them periodic table. So this periodic table of particle physics actually accounts only for about 5% of the total energy in the universe. And astrophysical evidence that it contains only 5% is actually pretty convincing. And this matter which does not shine, so it has to be neutral, it has to be stable, and only one candidate we know in the standard model which is like that is neutrino. But then for reasons which we will go into and which I will explain, neutrino cannot be the dark matter candidate, and therefore the experimental and theoretical understanding and information that we have from the dark matter, we actually know that there is at least one particle beyond the standard model, and that is the dark matter particle. And we are able to draw this conclusion only because we understand the interactions that all the standard model particles have in all the details. So here is the total energy budget of the universe, and as you can see, about 4.9% is the baryonic matter, which is made from the members of the periodic table, the quarks and the electrons mainly. And here is actually the almost 27% of the total energy is made up of dark matter that does not shine, does not have electromagnetic interaction, and this big piece, 68.3%, I'm not even going to talk about. All right. So where did the evidence for dark matter, or even the idea of dark matter, came? It began actually really very early. It began from Lord Kelvin, but for most of us, it begins from Zwicky, who what he did is a very simple thing, that he used virial theorem, and you are looking at the velocities of galaxies, and then he said if the galaxies are moving in this velocity, with this velocity, he wanted to equate the kinetic energy of these galaxies with the potential energy, as we know that's what virial theorem says. And then one found that the potential energy, which would be provided by gravitation, the luminous mass was simply not enough to provide that much gravitational energy, and therefore the galaxies should have just flown apart, and they were not flying apart, they were still moving, and that's really meant that there was more mass than the visible mass in the galaxy. And this was actually, this whole observation was firmly put in place with a lot of very detailed observation by Vera Rubin and Ford. So this is something very simple idea, so we can just go through it very quickly. That for the first time, these rotational curves were measured for something called the spiral galaxies, which happen to be the most common among galaxies. And here I have done a sort of a very cartoon of a spiral galaxy. And let me say that there is a star n, which is at a distance Rn, and then there is another star f, which is at a distance Rf, and Rf is bigger than Rn, so obviously f is far, and n is near. Now, by using simple laws of the gravitation, you can show that the velocity of rotation of these stars closer to, as a function of distance r, will be given by g times m by r, where g is the Newton's gravitational constant, m is the total mass that is enclosed inside the orbit of this star. And if you have RF equal to 4Rn, by this formula, the far star should rotate twice as slower than this one. But in reality, life is very different. And this basically, this was similar to the conclusion that Zwicky had drawn from his observations, because if in reality the stars which are further apart are not rotating slower, this means that the enclosed mass must also be increasing as the radius r of the orbit is increasing. This is a very simplistic explanation, but therefore it says that without dark matter, one should have expected the velocity of rotation to go like this, whereas the observed one was more like this. Now this is of course a cartoon again, and let me show you the original picture from the paper by from a review, and in which the original numbers of Rubin and Ford are actually presented, and this is sort of to guide the eye, and this is the rotational velocity in kilometers per second, and this is the radius. And now you see in fact that this is what was happening, that instead of falling much more sharply when we compare with how much mass was enclosed here, and then much later more experiments even showed this red dots show that it's very constant. This is for the galaxy M31. For galaxy M33, much better, much more accurate measurements have since then been made. And again, this is velocity in kilometers per second. Again, you see that this is what you would have expected if the mass around which the stars were rotating would have been only the visible mass, and in reality this is what was happening to the rotational speeds, and there were different types of measurements from different methods. I'm not really going to go into it because I'm not a experimental astronomer who understands these details, but I understand the principle and what it say. And this, just note, the distance scales here are of the order of kiloparsec. Remember, a parsec was 3.27 light years. And then since then there has been more evidence. So this is sort of a very firm evidence that this is what you would have expected if there was no dark matter. This is what you experimentally see. So clearly there is dark matter, and evidence of dark matter and the levels of galaxies has been actually compiled from a lot of measurements of the rotational curves. But it is not restricted only to the galaxies. In fact, one has observed collisions of galaxies in galaxy clusters, and I will explain this a little more in the next slide, but most probably I can just use this check picture. So this picture shows a collision of two galaxies in a bullet cluster, and what is shown in blue is the image of the collision that you got through gravitational lensing. So gravitational lensing is like you are looking at the galaxy or whatever cluster, whatever you are seeing, through the light that's coming, but at the gravitational lensing means that it actually getting modified by around some heavy object, and the effect of the gravitational field sort of gives you the picture, and that this is seen through gravitational lensing, and this is seen through X-rays. And indeed you see that there is more invisible matter that is clear in these galaxy collisions. And last but not the least is the last evidence for the dark matter. So, okay, to begin with, this is at the megaparsec scale, and the last evidence that I will mention is from the Planck experiment, which measured the cosmic microwave background radiation, particularly the anisotropy in this, because this is basically a picturization of the anisotropy in the temperature of the cosmic microwave background radiation, and this actually carries the memory at the time of structure formation and gives us information from that era, and this requires again the evidence, the existence of dark matter. So again, what I have said here, that what I said in the picture is written on the screen, but the point is that in bullet cluster, people saw the galaxy collisions, and as I said, blue was the picture obtained using gravitational lensing, red was the image obtained in X-rays, and one saw that there is more matters in the clusters than we could see. Now, after that, more and more distant galaxy clusters have been seen via gravitational lensing. And this gravitational lensing, as I said, is a bit like looking at crystal structure through diffraction patterns. But all of these have given us incontrovertible evidence of dark matter. And indeed, the measurements of cosmic microwave background radiation anisotropy has actually gave us the existence of dark matter at the scale of visible universe, which is, as I said, gigaparsec. This is a long story of astrophysics and cosmology in itself, for which I won't have the time, but I would give some indicators and pointers as we go along. So, once again, to combine, there is evidence for dark matter at all scales, at kiloparsecs from the galaxies, the rotational curves, clusters of galaxies at the scale of megaparsec, and at the level of gigaparsec from the cosmic microwave background radiation. Of course, we have dark matter even on the Earth and the Sun, but that density is very small. The local density is very small, but its density is much higher in places like dwarf galaxies or galaxy centers. Now, what do we know about dark matter? First, I have said it exists. It exists because of astrophysical observations, astronomical observations. Now, from the Planck experiment, we actually know that it forms about 27% of the energy budget of the universe. Remember, the dark matter velocities are about 200 kilometers per second. This is again comes from the astronomical measurements. And what we have as a direct experimental evidence, all that I have talked so far, all of which comes only sort of talks for the gravitational interaction. They have gravitational interaction. This is what we realize. And it is electromagnetically neutral, and it has got to be stable on the scale of the life of the universe, that is few billion years. And why does it have to happen? Because it actually has implications for the structure formation in the early universe, and therefore it has been produced in the early universe but has lived since then, so it has to be really stable on that scale. So this is a picture of the history of the universe as the astrophysicists and cosmologists have put it together. I have taken this picture from the PDG of 2014, and you see here that the first after the Big Bang, the universe was just radiation, and slowly the radiation was producing particles and antiparticles, and in this era, about time of 10 to the minus 10 seconds, really all you had was a soup of all kinds of particles and the radiation that you expect in the standard model, maybe even more, which we don't even know right now. Then around time of about some more seconds, 10 to the minus 4 seconds, indeed, in fact, we have the story where the nucleons formed, and at the end of the 3 minutes, the famous 3 minutes of Steven Weinberg, the nucleus had formed, and then it evolved. There were many other stages in the universe evolution, which I don't want to go into. And then this is the cosmic microwave background radiation, which became visible, and that's about 3 into 10 to the 5 years after the Big Bang. And this is the signals from this era have reached us in the Planck experiment. And then, of course, slowly the galaxies formed, the stars first formed, and here we are billions of years after. So this is how the universe has evolved from what is told to us by cosmologists and astrophysicists. And as I said, the laws of particle physics have actually, and nuclear physics, have implications as to what happened here. They were giving inputs to some different processes that were happening in this era. So in the earlier radiation-dominated era, the dark matter particles were also created, among other things, like the Ws, the Zs, the quarks, electrons, protons, and electrons and muons. In that era, you were producing also all the elementary particles, and they were in equilibrium with radiation. That is, there was a forward and backward reaction, which was happening at the same rate. And in an expanding and cooling universe, baryons then got formed, and structures such as stars and galaxies were formed. This is this picture that I told you about. Now, if the rate and creation, as I said, that since the universe is expanding Actually, what happens is that beyond a certain time, the created particles cannot find their partners to annihilate. So an electron doesn't necessarily find a E plus to annihilate and produce radiation. So at that point, for that matter, that particular species will fall out of thermal equilibrium with radiation, and then the abundance of that species will not change. The numbers cannot change because the particles are not annihilating, because they cannot find a partner to annihilate with. The temperature at which this will happen is called the decoupling temperature, and this will be determined by particle physics. It will be determined by the mass, it will be determined by the interactions that this particle has. So, and then these relics are kind of left over from the early universe, and since dark matter was created in that early universe, it must have had some interactions other than gravitation. We just don't quite know what those interactions can be, and that is the puzzle. Okay, that is the puzzle why this is important and interesting to particle physicists as well. Now, what is very important is that these dark matter particles actually provide the gravitational potential well, where all the matter gets together and then the structures like stars and galaxies are formed. So that is why the cosmic microwave background radiation gives us information about how much dark matter, which is cold, that we need. I'm going to explain the concept of cold in half a minute. So the expected Rayleigh density that we calculate from here is determined by the theoretical understanding of the early universe. That is how things happen in this early universe. That is something that cosmologists will tell you more about. And it also depends on the laws of interaction between particles and the particle content of the early universe and their interactions. So this dark matter Rayleigh density is truly what we call an astroparticle physics object. Both astrophysics, cosmic cosmology, and particle physics all are required, or it can shed light on all these three subjects. And as I tried to explain here, through our current understanding of cosmology of the early universe, we believe and think that the dark matter particles have to have had some other interaction other than the gravitational interaction. Now, do we know any observation? Can we infer from our observations what is the mass of this dark matter particle, which would fall? What is liked as a particle which would fall out of thermal equilibrium with radiation in the early universe when it is non-relativistic. This is what actually the cosmology tells us, and the fact that the structure formation happens because with dark matter. And it is because of this that the neutrino, which we know to have a very small mass, cannot be the dark matter. And therefore, that is what I meant in the initially, that the existence of dark matter actually tells us that there must be one particle which is a BSM particle. And this heavier dark matter candidate is called the cold dark matter. And such a weak, and this has to be, I will explain in the next two slides, such a heavy cold dark matter has to be weakly interacting, and therefore the weakly interacting massive particle paradigm for dark matter has really ruled for a long time. It's under a lot of stress now, but particle physicists absolutely loved it when it came. Let me spend a few minutes on this because after all I'm a particle physicist, and that's where my interaction with dark matter really began. So the Planck measurements and the anisotropies of the cosmic microwave background radiation actually tell us that the total energy density in the dark matter in certain units times the Hubble constant in dimensionless units is about 0.120 plus minus 0.001, very accurate measurement. I remember a time when this number was 0.3, so with big errors. So indeed, these cosmological observations have come a long, long way. Let me call the candidate dark matter particle chi. In a theoretical model, one can compute, again using cosmology, that omega chi h square is nothing but, it's a long, long calculation, is 3 into 10 to the minus 27 centimeter square plus per second divided by the annihilation cross section, which is times velocity averaged over the velocity distribution of all the dark matter particles. And the couplings of the dark matter particle and the mass together decides the sigma annihilation, and therefore this value will decide what is the Rayleigh density, and thus the Rayleigh density that you predict in the model depends on this all important quantity, and different combinations of the coupling constant and the mass of the dark matter particle can produce the same annihilation cross-section times velocity average. And this is what is controlled by the particle physics model. And now if you have this to be 0.120 plus minus 001, then you need a particle physics model which will give this to be of the order of 10 to the minus 26 centimeters square per second. And indeed, lo and behold, particle physics actually had an extremely well motivated model for cold dark matter, and that is supersymmetry. This was actually the solution to keep the theoretical solution to keep the Higgs boson light. And this was saying that associated with every particle, there is a supersymmetric partner. And for the symmetry to solve all the aesthetic problems of the standard model that I told you, it needed the existence of new particles whose masses were less than about 1000 GeV. And one way was to look for them at the LHC. And the LHC has not found any evidence of those partners so far. This is what I meant when I said that particle physics has a crisis with the good and the bad. But at the same time, this theory actually has very ready-made dark matter candidate particles. So enthusiasts like me and many others would then say that, aha, maybe we have not found supersymmetric partners of top quarks which should have existed less than 1000 GeV, but maybe the dark matter particle, which is light, is still existent, and I can look for that window, look for that at the LHC. And we had discussed some of this in this textbook which we wrote many decades ago now. So in the simplest extension of the standard model, which is supersymmetric, there exists naturally a particle which is neutral, stable, has actually annihilation cross-section which is of the order of 10 to the minus 26 centimeters second inverse. And lo and behold, this is precisely why we were all very excited decades ago when people said that this is the mass and the interaction cross-section that the dark matter particle must have. And this is where the idea of the WIMP had really taken hold of all of us. And unfortunately, we still don't have evidence for the existence of WIMP. Also, more importantly, however well motivated, this is just one model. So from astrophysical and cosmological arguments and all the other measurements, we have no real confirmed indicator of the mass of this dark matter particle. So there is a range of mass that is allowed, and for different ranges, there are different models. And the important thing, of course, is that no matter what its mass and what the model, they also have to give rise to a Rayleigh abundance that is in agreement with this extremely accurate measurement. So these are two requirements of the model, and therefore there are two parameters. One is the dark matter mass, and other is the annihilation cross section. And this really depends on the particle physics model and on the particles present in the model. So in fact, I have stolen this slide from my friend Hitoshi Murayama, who shows that in principle there is a mass range, and you forget what units those are. You don't need to know this. All you realize is that there are 36 orders of magnitude of the allowed mass ranges of the dark matter particle. And there are, of course, many models, and this is the archive preprint from which I have taken this. I told you there were two parameters, the mass and the cross section. And there are a large number of models which inhibit different spaces in this plot. And this is the reason why it's very difficult to make a statement about dark matter in all generality. But I must warn you, not all the models give signatures at the LHC, and not all the models are necessarily well motivated. Supersymmetry happens to be a very well motivated model and happens to give some very nice signatures at the LHC. So how to decide which part of the story is correct, if any? I've given you these, there's a variety of these models. I've told you my favorite model, but that is neither here nor there. So there are some who argue actually that simply modifying theory of gravity will be enough to explain the dark matter, but I'm not going to go there, and that is not what I'm going to be discussing. But this is just to tell you the difficulty of solving this problem, and therefore not only we have to look for the dark matter, and if we find any evidence, then we have to figure out which one of this multitude of ideas is right. Now, in general, there are three different ways in which you can study dark matter. One is what is called very, very picturesquely, shake it. This simply means that a dark matter particle is incident on a nucleus, the nucleus vibrates, gives actually the elastic scattering, and there are certain signals, and you look for the evidence of scattering of the dark matter particle from the standard model particle. You can try to break it, in which case two dark matter particles annihilate and produce standard model particles, replicating the reactions that would have happened in the early universe and which still happen today, let's say in some star at the center, can happen at the center of a star, or can happen in various astrophysical situations. And then there is the one that is something that we can do on Earth, and that is collider production. You collide standard model particles and produce a pair of dark matter particles. And there are, of course, very many experiments and big experiments, big detectors. One is a direct detection experiment. I have shown you here. This is happening when you shake it. Then this is the make the dark matter. This is the LHC, and this is the picture from CMS detector. And here this is called indirect detection, and this indirect detection is coming from breaking it. Okay, so these are the three different types of experiments, large number of very different experiments which are trying to look at different regions of the masses, and the interactions of the dark matter particle are actually in progress, in planning, and this is a very, very rich and very, very busy area. And I will refer to mainly here, but maybe a little bit before, to this direct detection. So how do we detect it on the Earth? This kind of thing, as I said, the WIMP comes and gets scattered of a nucleus, and the WIMP goes away, and you see the recoil energy of the nucleus, and that's what you measure. It's an extremely difficult experiment, and the expected recoil energies are about 100 keV. This method works if the dark matter mass, particle mass, is between about 10 to 1000 times the mass of the proton. So for those who understand, the mass is between 10 GeV and 1000 GeV roughly. In that mass range, the recoil energies are up to 100 keV. Even those are very difficult to measure, but we have very clever experimentalists, and they have been doing these measurements. I will show you a plot of the results that they have obtained, and this is very recent. And now people are thinking of modifying the detection techniques for lighter dark matter particles, make it more efficient for lighter dark matter particle. There is a lot of development, and as a theorist, for example, as a phenomenologist, as a person who is trying to understand the basic phenomena, as a theorist, our job, most of us, our jobs is to find other motivations for looking at small mass or the light dark matter particle, or are there motivations to try to increase the sensitivity for large masses. So that is the kind of role that a phenomenologist will have to play, and that's who I happen to be. So this is the latest result from the dark matter experiment that's available, and this is in particle data book. You can go and look at it. And now what it tells you is that the latest experiment tells you that if there is a WIMP, then for a given mass, there is an upper limit on the cross section that the WIMP and nucleon can have. So indirectly, it's constraining the models of the dark matter. And even from 2017 to 2019, you see there has been an improvement of 1 order of magnitude in the limits that were being produced by these experiments. I will tell you a little more, if time permits, about the impact it had on one analysis, that WIMP theory analysis that we had done. So, we had designed the Large Hadron Collider to find the Higgs, but one had also hoped for more. So many, many decades ago, when I was a young physicist, which is really decades ago, the LHC was on the horizon, and there were these three big mountains: the dark matter, the baryonic symmetry in the universe, the Higgs. They were the various, peaks to be conquered. Now, slowly, we have arrived at the Higgs peak, And then we have realized that the distance had belied us, that really separation between this Higgs peak and these two peaks, and these two peaks are still inaccessible. We still have to move forward. And having done this in the last 15 minutes of my talk, I'm going to now concentrate on the small part of the story, that is, how can one probe the dark matter candidate in supersymmetry, only in the context of supersymmetry, through the joint explorations at the Large Hadron Collider, in the direct detection experiments that I showed you, and the upcoming future E plus E minus colliders. So I'm not covering so much the indirect detection, and I'm not covering the whole model space, just one particular model. So I'm going to discuss it particularly in the context of a model called supersymmetry, which I showed you already. It's a minimal extension of the standard model called, which is supersymmetric, is called MSSM, Minimal Supersymmetric Standard Model. And I will look at two avatars of this MSSM. One is called Phenomenological Minimal Supersymmetric Standard Model, and one is called Next to Minimal Supersymmetric Standard Model. Each one of them have about 20. First has about 19 parameters, and the second has about 24. So you would say, oh my God, go away. You are talking of a model which has so many free parameters. But luckily, there are only 3 or 4 of those parameters that are relevant for the dark matter phenomenology, and that's what makes the subject tractable. And the advantage is that this is a predictions for the relic density, the direct detection cross sections, and the LHC searches. All are decided by the same few parameters. Therefore, we can study the model through its implications for all the 3 different experiments. So in some sense, we have many different windows, and we can look at the same model, and we can try to draw a better conclusion about the shape of the object, which is hidden to us by the walls otherwise. Of course, the direct and indirect detection experiments do not really depend on what your model is for the dark matter, because, for example, you saw the direct detection example that I gave you. Voila. You just have to know kinetic effect of this. You're measuring a kinetic effect. The interpretation of that will depend on the model. Whereas at the Large Hadron Collider, some of the signals are independent of the dark matter model, and some are actually dependent on the dark matter model. So let me give you, some examples. So first model, I call it model independent ways at LHC number 101. So just to tell you, today the Large Hadron Collider has produced about 7 million Higgses. Of course, not all of them can be detected, but this just tells us that the studies at the LHC now have turned towards looking at rare decays of the Higgs boson. That means if the Higgs boson decays into a particular final state, it's a very rare event. If it happens once in 1,000 decays, we have produced 7 million. So we are going to see a few of those decays no matter what. So one can ask a question, will there be additional exotic decays of the Higgs for the particular BSM that you are looking at? And the particular BSM I am looking at is supersymmetry. So I'm in general going to talk about the decays of Higgs into dark matter particles which cannot be seen in the detectors. Just like the dark matter cannot be seen by the eye, the dark matter particles, because they don't have electromagnetic interactions, and any detection so far in the collider environment is through the electromagnetic interactions of the particle. These kind of dark matter particles will be invisible to the detector. And the question is, how can you make this invisible visible? That was the question that we had asked ourselves, and I'm going to tell you about that. One of the people who asked this question was us, but many others did the same. Now, the dark matter particles actually, as I said, do not leave tracks in the detector. So their production is actually indicated by an imbalance of the moment. So it produces events with a momentum imbalance, and that's called missing transverse energy. Now, the signature, I told you at the LHC, there were 2 types of signatures of the dark matter. One which depend on the model, and some things that do not necessarily depend on the model, that is the signal. The interpretation will depend on the model. Now, in the cascade decays of the new heavy particles that exist in the model, in SUSY, there are such heavy particles which have strong interactions, and they are called gluinos or squarks. Now, when these gluinos or the squarks, if they exist and if they are produced, they will decay. But in the decay chain, they will have to be, at the end of the day, a neutral, invisible, lightest supersymmetric particle, and that it cannot decay further, so it's stable. And right now people have looked for it because that was looking under the lamp, and as soon as LHC was turned on, one did a lot of searches for this, and in the 10 years now, experiments have yet not found anything and have only constrained the parameters of the masses of these strongly interacting new particles. So for the time being, let me forget about it. The current data still allows the possibility of lighter new particles which could have been missed because their interactions were not strong. This is one of the reasons by which they might have been missed. So now if they were missed in the early low energy or the run still now, when we have a higher energy or a higher luminosity run, maybe we have a shot at them, and that is the direct detection of these brothers and sisters of the dark matter particles, which actually do not have strong interactions. Now the specific signatures of these brothers and sisters of the dark matter particle that I will talk about will actually depend on our model. So my model, which is SUSY, I will have a set of signatures for my experimental friends for the production of charginos and neutralinos. This is what for the cognoscenti. Whereas in a model with extra dimensions, one might have some other particular signature. So this is dependent on the model. This is dependent on the model. But there are model independent search strategies that we can suggest. And that has to do with how dark matter particles can be produced in association with other standard model particles. And I have an example here. In a proton-proton collision, you produce a Higgs and a Z boson. And the Higgs actually decays into two dark matter particles. Such decays are possible in SUSY. And then, or any other dark matter model which has couplings to the Higgs. And then you will have events, either there is a Z or the W or the jet, and then there is nothing in the detector. So that is called a mono Z or W or a mono jet production. And this is, you can do this, or you can actually look for the production of a Higgs, PP, producing a Higgs and a Z, and then you say my Higgs decays into particles like this, and I detect only the Z, and can I then find out information about how often such a decay would happen? So in the current situation, there are two possibilities to look for the light dark matter that I can see. One is by looking for these mono events, and one of them, for me particularly, I focused on was looking for an invisibly decaying Higgs. It need not be always an on-shell Higgs decaying into a pair of neutralinos. There are other processes, I said this is an example, there are other processes which will also produce a Z with a pair of neutralinos, or Z with a single neutralino with a pair of neutralinos, but I'm not going to talk about it here, but that also exists. So looking for these mono events is one big sure way of looking for the dark matter candidate. If the dark matter candidate has a mass less than half the Higgs mass, then I can look for it for the invisibly decaying Higgs, and otherwise I can look for the phenomenology of the neutralinos and the charginos, or the brothers and sisters of the dark matter particle, which have so far gone undetected. So there are two different ways. These two different ways, here I should have added look for invisibly decaying Higgs / look for mono events. So both are two aspects of the same physics. So these are model independent searches. These are kind of here the searches that I will suggest will depend very much on the model. In the past few decades or so, with my group, with a variety of students and postdocs, we had been doing different kinds of works, and don't worry, I'm not going to tell you much about it. I have only 5 more minutes left. So in that 5 more minutes, I want to give you a flavor of how one will do research on this subject, and what is the main lesson that I want to draw from my studies, which I want to take further. So I will try to only indicate to you what the work was. Anyway, that's what I had planned. So one is to how to look for the dark matter at the colliders to the Higgs decay. And that's what we had done here. So in fact, in this, this was one set of papers, and the other set of papers was what I said is that the lack of signals for SUSY particles at the Large Hadron Collider had generally pushed the region of explorations of SUSY dark matter to larger masses beyond 100 and 200 GeV, and that made a lot of theoretical physicists very unhappy, because they said, oh my God, if SUSY is heavy, if it goes beyond 1 TeV, then this is not going to solve my problem of instability of the Higgs mass. So whether SUSY has anything to do with particle physics. So before we draw those conclusions, or before we ask such questions, I wanted to ask critically how a light supersymmetric dark matter and is it still allowed? And by light, I mean, I have really focused on light, meaning smaller than half the Higgs mass, but people have looked at other things also. And then I asked the question, firstly, how can you look for such a dark matter particle at the LHC through the invisible Higgs decays? And then how can you look for its partners? And that is like two different parts of our investigations. And the second part of investigation is more recent, and that resulted in this review as well as these papers. But again, that is not what I'm going to discuss in detail. But this I like, because this is actually, I think we were the first one to actually suggest this, and it was followed by the experiments, and then there were counterparts of this suggestion which came much later, somewhat later, not very much later. And this was a paper we wrote in 2003, and this time we didn't even know whether the Higgs existed. We didn't know the mass of the Higgs. For a variety of the masses of the Higgs, and for a variety of the values of the probability that the Higgs will have invisible decay modes, we kind of tried to figure out how one can make the invisible Higgs visible by looking at this Z boson. So what you are seeing in your detector is only a Z boson or a W boson with its momentum being balanced by something that doesn't leave a track in the detector. And could the experimentalists look for something like this? Indeed, our CMS friends have taken a plot, actually event display, where they have a Higgs which decays into a BB bar and produced in association with a Z which decays into a nu bar and which recoils, again missing energy. So they can indeed do this, and therefore they were able to do the search that we had suggested. And actually in our update of the paper, we had projected that at the LHC with 8 TeV energy with 20 femtobarn inverse, we might be able to push the limit for the invisible branching ratio of the Higgs to about 0.58. And I was very happy when, by an accident, in the first paper in 2014, the experimentalists actually had the upper limit. They said that obviously they have not seen such invisible decays, and therefore they have put a limit of 0.58. And what we had said is that if the branching ratio was bigger than 0.58, one should have seen a signal at 8 TeV at 20 inverse femtobarn. The experimentalists, being much smarter than us, they arrived at that number even much before the 20 femtobarn inverse or the 8 TeV was arisen. But this has now this has become very good channel for looking for invisible decays and more along with this. And indeed, at the Large Hadron Collider, at the highest luminosity, we will be able to reach the limit of 0. In this language with 0.58, here it will be 0.04. So if the branching ratio is as small as 0.038, the Large Hadron Collider would be able to see that invisible decay of the Higgs. Indeed, I just want to show you that our experimentalists are really smart, and they are able to, and they have actually observed an event where there is a big jet, high energy jet, which is actually a TeV jet, which is recoiling against the missing energy. Sadly, this can be explained by the standard model processes. So they have to keep on looking and see whether they get an excess over the standard model background. Now, what is the use for a theorist of all this? So this was, as I said, a model independent statement. But how do I translate it for the model of my interest? Now that is very simple. In each model, the invisible branching ratio actually is related to the total number, to the relic density also. And the fact that you must produce the right relic actually rules out some of the values of the parameters of the model. And then the invisible branching ratio measurement have ruled out some other parameter points. And this is how then you can study and see whether you are able to probe the dark matter, that is the supersymmetric dark matter here, but it can be any other dark matter, through this kind of invisible decay modes which has interactions with the Higgs. We can do it here at the LHC. Just to show you, here we had taken a large number of points of the supersymmetric parameter space. And at that time, there were no direct detection experiment data to speak of, and therefore, the invisible branching ratio measurements at that time were also very small, only at the level of 10%. And we were able to say that all these points below this line are completely allowed. And we had said in future, the xenon experiments will be able to probe these regions. The x-axis is the mass of the dark matter, and this was the invisible branching ratio. Then came the dark matter detection experiments that I already showed you. And indeed, most of the allowed points got ruled out by this direct detection experiment, and only these points in the vicinity of 60 GeV in the minimal supersymmetric standard model are still allowed. And you can ask the question, can LHC look for it? And yes, indeed, LHC can look for it through the associated production of the supersymmetric electroweak particles. And indeed, we have shown that the Large Hadron Collider with the 300 inverse femtobarn will actually be able to probe some of these regions. The blue means that LHC will be able to probe it. The orange points mean that you require the next generation LHC runs. So, all this is happening and it's very exciting. And in the case of NMSSM, for which I'm not going to show you the results, in fact, the allowed value of here, for example, the only allowed value for the neutralino mass seems to be in this small window around 62 GeV, and that too will be probed completely at the high energy and high luminosity LHC. But if it's NMSSM, actually the entire region here beginning from 1 GeV is still allowed, and therefore in the context of NMSSM, we don't seem to be able to rule out a light dark matter particle, and therefore the detection experiments which are trying to set up detection of light dark matter particle will become very, very important. I am running desperately out of time, so let me now, however, tell only one last thing, that in all this, you remember I told you that we had to choose only that region of the parameter space where it gave rise to the correct relic density, okay, or at least less than the relic density. But that is dependent on the model of cosmology, and we don't have complete knowledge of early cosmology. So if it is non-standard cosmology, then the more parameter space of my SUSY model gets allowed, and in this case, the experiments at the colliders at the LHC will be able to probe it, and even if then it will be allowed, the LHC experiments and the ILC experiments will be able to probe that region. So in some sense, it's very exciting that even a non-standard cosmology scenario, it would be possible to hint for and confirm or otherwise bias LHC searches of the partners, the brothers and sisters of the WIMPs, the charged and the heavier brothers of the WIMP. So therefore, looking for WIMPs at the Large Hadron Collider is definitely worth it, even in the regions that are not allowed by standard cosmology. Now there were a few more plots which I won't have time, so I will skip them. I have done the similar studies for the NMSSM, and now I have seen and we have shown that the WIMP paradigm for a light LSB is allowed by all the current data and all the theory, all the relic density calculations, and one can test them at the high luminosity, high energy LHC, at the International Linear Collider or CEPC or FCCEE, and the future direct detection experiments. The only thing I want to show you here is that, for example, it is this region at the very small masses, especially when the cosmology is not standard, this region is not something that the direct detection experiments will be able to probe, and that is where the new experiments which probe the small mass dark matter are very, very important. And it is interesting that in this region, LHC can make inroads, and we already showed that the current LHC data rules this region out, and the future LHC data will rule even this distance region out, but we still are left with these regions of small mass dark matter, and indeed, therefore, explorations in this region are theoretically and are very, very well motivated. And as I said, even the non-standard cosmology scenarios can be tested, and the rage of the day is to do model independent analysis, but that is a separate talk and a separate discussion. All I want to say is that the quest continues. We all walk, and hopefully we will reach the end, if not in next few years, maybe in the next decade, through the variety of experiments of the dark matter detection, the LHC, and the xenon 110 or xenon n10, and Lux and Panda, and so on and so forth. So to me, future is bright. Thank you very much. And sorry to have taken 5 more minutes than I thought.
Thank you ever so much. That was an incredible talk. I think we all learned a lot from that in just an hour. It was a really fascinating journey through the dark matter research, especially at the LHC. We've already had quite a few questions come up, and what I'm going to do is go through those one by one. If anyone would like to ask another question, please do post it into the Q&A window, and we will get around to them if and when we can. So I'd like to start, there's a couple on a related issue from the earlier part of your talk. So I think I'll start with those first from the audience. So we've got one question. You said that the Earth and the Sun also have dark matter. How much dark matter is there compared to baryonic matter in our solar system?
I don't have a numerical answer, but it's extremely, extremely small. But I'm sorry, I don't have the quantitative answer. And that has to do with the fact that we don't have, neither the Earth or the Sun have too much mass to hold that stupid dark matter together, But Earth, at the center of the Sun, there might be some dark matter, but at present I cannot quote a number, but it's rather small.
And another question which is quite related is, what is the distribution of dark matter in a galaxy compared to visible matter? Now, of course, there's no such thing as an average galaxy.
That is the point. You answered it for me. You answered it for me. Actually, no, but even then, I think people do try to, it is the cosmologists, and it is really in the realm of the cosmologist and the astrophysicist. I don't believe that the dark matter, distribution of the dark matter is correlated with that of the visible matter, but there are sort of these things can be kind of got at only by detailed simulations of galaxy formations and the structure formations, and there it depends on whether the dark matter is collisionless, whether it is collisional, and there are all kinds of stories where there what is used normally is the one profile which has been determined by the astrophysicists and blessed by them, and this is what we would all particle physicists would use it. But I think the cosmologists and the astrophysicists are continuously working on to give us a realistic dark matter profile and that distribution profile, and I think it really is something that's not very well known. So that's an active area of research.
Thank you. And I think that answers part of Brian's question as well. Another question, if dark matter is found in the next years, what are the implications for future colliders?
Okay, I think it's a very nice question. And as I said, it depends really on the mass of the dark matter particle, because the kind of that is why I kind of made this big presentation about the light dark matter particle, that if, for example, there are indications, and astrophysically there are a lot of indications of some light dark matter particle. Unfortunately, astrophysics, there are also a lot of astrophysical uncertainties, and therefore we don't know how much to trust them. But if it is a small mass dark matter particle, then as I have tried to portray, the colliders like a low energy FCC, I mean 500 GeV is low, 230 GeV or 300 GeV is a low energy machine, CEPC of 235 GeV or FCCEE or ILC would already be able to throw some light on the associated physics. But I think the most important order of the day, if LHC were to find it, I have a feeling that first we will have to then try to analyze the different signatures or lack of signatures at the LHC in a coherent fashion to get some information about the underlying model. And until and unless we get an understanding of these underlying models, some direction to it, I don't think we can easily give an answer about where next, Archanaji. So I'm a bit sorry that it is not very conclusive, but that's what we are all trying to do.
Thank you.
Theorists, okay. But I agree with you that that's a very important question to ask. And I mean, there are two different kinds of questions. That firstly, in the context of dark matter, firstly, does it exist? If it exists, does it have anything to do with particle physics? If it has to do with particle physics, and if I discover, so that is the second question that I was saying, that even if I find something, I have to prove that it has something to do with particle physics. So if I find it at the LHC, then I know for sure it has something to do with particle physics, or even if I see it in direct detection experiments. But after that, my path becomes really slow to try to make a jump to the colliders. Okay.
So sort of related to the previous question, could we use the density of dark matter variation density in dark matter where we know it to be, to help us to work out how to detect it?
I don't really think so, to be honest, because all our astrophysical or astronomical ways of detecting dark matter, or even these direct detection experiments, are kind of, firstly, the rates that we are looking at are extremely small, and I think we are first struggling to get an evidence at all, and then to think of density variations and so on is really the, how should I say, it's really the next order of complexity. And right now I think we are all stumped that simple detections are simply not working. And I mean, it's amazing how difficult those experiments themselves are. That is xenon. I have heard talks by xenon, and I think it's I mean, to me, the level of complexity in the experimentation is about the same as when people were doing neutrino experiments in the early decades, when you were trying to, Reines was trying to detect solar neutrinos, let's say, or Steinberger was trying to detect neutrinos for the first time by using the hull of a ship. So I think we are somewhere at that stage for dark matter detection, I feel. So the complexity of the experimentation that is required is very high. I completely agree that the question is a very correct question, but I think that level of detail, we don't even know how to address that. In our computations of structure formation, we can address those questions. Though are very difficult computations, but I think our astrophysics friends are much able to tell you what is the profile of the dark matter and what would be the variation in the core of a dwarf galaxy. They are able to do it perhaps much better. At least that's my, I mean, this is maybe a case where theorists are, in astrophysicists at least, particle theorists are not ahead of experimentalists, but I think astrophysicists are ahead of, in understanding the dark matter. The theorists are perhaps a bit way ahead.
Well, you bring up their neutrinos, a topic very close to my heart. So if I may take chair's privilege, in the direct detection paradigm, we are getting closer now to the so-called neutrino floor, or perhaps more popular nowadays, the neutrino fog. So if we don't discover WIMPs in that region, what impact, if any, would this have on collider searches and searches at the LHC?
Okay. No, actually, that's again an extremely valid question. And if the masses, that, I mean, maybe I cannot, because as you notice, I'm no longer sharing my slide, But if you notice the neutrino flow, maybe can I just share that plot because I might be able to answer
Please
your
do.
question. So will you permit me again to share the screen? I will because I think with a picture, it's always, picture is worth a few thousand words. So here you see that if, for example, if we, this is the point I was trying to make. It depends on where we reach the coherent neutrino scattering floor. If it is for a dark matter particle of mass 10 GeV, then I tried to make a case that LHC still has a chance of looking at those regions. Okay. Whereas if we see a process, if you put a limit here at this range, then I think LHC's chances of probing in this region are still also not very bad. But the real place where LHC keeps running out of events will be when the masses go to 1 or 2 TeV. So in this region and in these regions, LHC still has a chance to look for dark matter particle through the associated particle phenomenology. And like this, here, as I said, the light associated electroweak particle searches, if they exist in your model, that will be here, and therefore, thus the direct detection reaching the neutrino floor here may not be all that conclusive. Okay?
Thank you.
Have I answered your question?
Yes, I think so. I think so. Absolutely. Another question.
I mean, that is part of my reason for focusing on this region, to be honest.
Yeah. Another question which we have from the audience, which I think is something also very close to my heart. So I'm going to pick on that one. What effect, if any, would the detection of dark matter have on our understanding of the matter-antimatter asymmetry of the universe?
Okay. Now, I would say in a general picture, I don't think there is a relationship between the dark matter and the matter baryon-antibaryon asymmetry. But there are people who have constructed models where the dark matter indeed has actually CP violation, and then in principle it can have some relationship with the baryon-antibaryon asymmetry, but all that is extremely model dependent, and a general model independent answer cannot be given to this question. Okay.
Yeah, thank you. I thought you were going to say that, but it's good to hear. Okay. Another question, two sort of related questions that I'm going to put together. So we've got one audience member who's asking if there is a sort of elementary particle list for dark matter. You know, what are the best candidates at the moment of dark matter candidates on the market, as it were?
Okay, that is why I showed you that one plot and one reference. I think, I mean, everybody has his or her favorite dark matter particle. See, okay, it's like this. Actually, the standard philosophy now in the dark matter research, by and large, has been sort of a very model independent thing, where you postulate a dark matter candidate and a mediator, that has been the general philosophy these days, that the dark matter particle is outside the standard model framework, and there is a mediator through which this dark matter particle talks to the standard model particles. That's how it gets produced in the early universe. And then you introduce the minimal number of degrees of freedom in your model that you like. So it is a bit like trying to construct a model, trying to construct the first versions of your quark model, if you wish, okay, for the dark matter context. So there are people who think about axion as dark matter. There are people like me who think of neutralino as dark matter. There are people who think slightly extended MSSM, which has a right-handed neutrino, as dark matter. Some people think of sterile neutrinos as dark matter, and that is particularly interesting because sterile neutrinos, actually also in the context of extended MSSM, can actually have self-interactions. And then neutrinos can have self-interactions. And a self-interacting dark matter is not anymore collisionless, and therefore in the structure formation that have any implications. So what I think is that because of these many tentacles that the properties of dark matter have, there is a very vast variety of the table, everybody's favorite table for dark matter particle. But that's what makes it exciting. I mean, that's where the mess is, and that's where we should try to answer it.
Yeah, we do love a bit of mess. As soon as something's a bit messy, it's incredibly intriguing.
Now, as a matter of fact, we can follow the very big man, Steven Weinberg. He told students, go where the mess is.
Yes, yes. Okay, so another question. Can ordinary particles, is there the possibility for them to decay into dark matter?
They can decay into a pair of dark matter particles. They cannot decay into a single dark matter particle, because by and large, the dark matter particle, this is not a theorem, but by and large, a dark matter particle is dark matter because it's stable, because somehow its numbers are in a reaction process. There is some kind of discrete symmetry which does not allow a single standard model particle to decay into just one dark matter particle and many standard model particles. But we can have standard model particle decaying into a pair of dark matter particle, and the Higgs is an example. It really depends on the model of dark matter. And I will actually take, Melissa, if you don't mind, the question of Richard Banner, which is related to this. So may I take it up, because I see
going to ask it next. Go for it.
Yeah. So therefore, the point is that Higgs to chi1 naught chi1 naught is a single a standard model particle decaying into dark matter particles. So that's the answer to your question, Anju. And Dr. Richard, the answer to your question is that yes, indeed, there are considerations of the possibility that the dark matter does not interact with the Higgs field. But in that case, it can still give rise to the monojet and mono W events through some other process. Not with the process that I wrote, but you can still give rise to that kind of final state. And therefore, this search of monojet, mono-Z, mono-Higgs are very, very important. They are not restricted to the Higgs portal dark matter theory. I hope you get the answer to your question, Richard.
Well, I think that leads us on nicely to Fraser's question. How often are monojet events seen at the LHC?
Yeah, I think there have not been very many of them yet. And what has been seen are still consistent completely with standard model expectations. I mean, that's where the great theoretical expertise that we have got in computing what should happen when two protons collide and produce a jet of 1 TeV or 1.2 TeV. A lot of progress in QCD has been made. And I think at present, what we see is all consistent with what is predicted by QCD.
Thank you. Yeah, it's a very interesting answer to an interesting question. Slightly changing a little bit now into more astrophysical detection. So we have a question asking, how will dark matter be detected or observed astronomically in the future? Will technology used in astronomy and telescopes, will this need to improve or increase in sensitivity as dark matter doesn't interact with light? So can we expect something as we saw in the case of the EHT?
I really don't think so. I think the ways to detect dark matter are really the three that I showed you: shake it, make it, and break it. So light really does not play a role in detecting dark matter. But if you are asking whether we can combine together a large number of detectors, like we did this for EHT, a sort of coherent effect of different detectors, I really don't know. I mean, I will have to talk to a really good experimentalist to ask them these questions, but my guess is it would be very, very difficult. But I am no experimentalist, so I won't want to venture a guess.
Thank you. Okay, so the penultimate question that we have here, and I think we're a little bit over time, but I think we'll try to get through all of the questions because we're so close. What if the processes in the universe and in the LHC are simply not energetic enough to produce or detect dark matter? Do we have any theories giving us a sort of lower limit on the energies that must be met in order to produce dark matter particles? I think you touched upon this a bit in your talk. But
yeah, I did. I mean, we don't have knowledge on this or knowledge of this. I mean, that is why there is this limit, right? The limit on the mass of the dark matter. So we don't have a lower limit, we don't have a higher limit, almost. I mean, it's such a huge range, 36 orders of magnitude, and energies of over that range exist in the universe over its evolution somewhere or the other.
Indeed.
So if not today, they must have had significance in the, will have to be produced in the early universe. So I don't think we have anything like this. Melissa is still gone again. I think Melissa's Zoom has frozen.
Oh, well, sometimes I might freeze from time to time. I thought I would try going back on video, but
okay, good.
Apparently Zoom can't quite handle it, but I am here. I'm refusing
Very
to
good.
the duration of this session now so that we don't have any more delays. Okay, now the really final questions, please. So a second question from Fraser, and then we're going to move on to a slightly different topic. Could dark matter contribute to G-2 measurements?
Okay, the answer to this question, Fraser, is very similar to my answer about BAU. That I can certainly construct a model, and people have constructed models which simultaneously have dark matter, neutrino masses, and G-2 explanations. I mean, supersymmetry happens to be an example of that, okay? And for example, G-2 supersymmetric contributions involve, if not the dark matter particle, involve its cousin, namely the charginome. So in supersymmetry, a particular kind of supersymmetry, the G-2 contribution can come from a charginome loop. And that charginome will of course be a brother of neutralino, which is the dark matter. So in a given theoretical framework, which is broad enough, and I think as a supersymmetry expert, I used to all the time say that supersymmetry has in it possibility of addressing a variety of issues, and this is an example of that. That without having to construct a model for G-2 and construct a model for your dark matter, in the same given model, you have connections. And indeed that is true, Fraser, that yes, there are some models where there is a connection between the two solutions. But clearly they are not completely acceptable solutions. They are on the border of acceptability, 1 sigma, 2 sigma, all kinds of such things. But that is because we don't know the truth. And if anything I have learned from studying the history of standard model, I would say that I just want to take back a completely different track, that when V-A structure of electroweak currents was decided, when Feynman, Gell-Mann and Marshak and Sudarshan put forward the V-A theory, there were 5 different measurements of asymmetry, angular asymmetries in the polarized neutron decay. There were measurements of the angular asymmetry in the pion decay. And one agreed with V-A, one agreed with scalar and tensor. So we are, for dark matter theory or G-2 explanations, we are somewhere in that era. We have different ideas. One idea seems to work very well for one aspect, not for the other puzzle. So I think we have to move. That is what is meant by mess. But we have to move along, and we have to actually try to understand things in total. We have all got spoiled by standard model. One model explained everything beautifully. But we have to remember the dark ages before the standard model. And I think now we are in the dark ages after the standard model. So the kind of questions you are asking just tells us that there have to be relations between different puzzles we are seeing, but it's not, we are perhaps, and this is what I meant, it's a bit perhaps like an elephant, that one puzzle is showing you the trunk of the elephant, and the other puzzle is directing you to the leg of the elephant, and therefore you think that elephant is very thin, and the other one is saying that the elephant is very fat. So we don't know. I think in some sense I am actually completely excited about this, and that's why I'm so excited about research on dark matter, that it gives, and all these 3 puzzles that are in front of us right now.
So we are now completely out of time. Thank you so much. There is another question here about evidence for the observation of dark energy. Is there anything for it other than accelerating galaxies, which is beyond the scope of this talk? If you fancy taking it on, feel
Oh, I think Melissa got logged out.
Yeah, I think Melissa was going to say, if you fancy taking on the question, please feel free to, or
Oh, she's back.
Yeah, there she's back.
Okay, right. So it just decided to chuck me out and put me back in again. But perhaps my system's working a bit better now. It seems to be, so that's good. Cheeky question: if there was one take home that you wanted us to leave this talk thinking about with regards to dark matter at the LHC, what would your one message be to us in the audience today?
Please think about the low mass dark matter very seriously.
Thank you.
I mean, we need to close the window completely before we give up on simple supersymmetric dark matter.
Mm-hmm.
That's the...
So it's a very good and very topical point at the moment. So that is an excellent take home for everyone in the audience from your point of view. So thank you very, very much for that. So we are a little bit over time, but I think it was worth spending those extra minutes. I think we all got a lot out of it. Thank you so much for getting through all of those questions and for really fantastic slides. I should point out that we do actually have another 2 upcoming talks from Professor Rohini in the future. So on the 29th of October, we have a talk, Unravelling the Secrets of Nature from Rutherford to the LHC, and that's actually on Friday. And I have to say, I'm literally putting off my pub trip with my Cambridge group colleagues for this, because it sounds incredibly exciting. So Rohini is actually going to take us on a journey from Rutherford all the way through to the Higgs discovery at the LHC. And this is going to be a really fun and unique opportunity to learn all about this from Marina's point of view. So I hope you will all join me there on Friday. And in the future, at a date yet to be determined, Rohini will also be talking about one of her other passions, women in science in India, status and prospects. And you will get information about that from the IOP as soon as the date is set. So please do come along for those. Thank you again, excuse me. Thank you again, sincerely, Professor Rohini Godbole. It has been an absolute honor to share this time with you, and I look forward to seeing you on Friday. Thank you to all of our audience. Thank you for the fantastic questions, and thank you to the IOP for organizing and the IOP. See you on Friday.
Bye-bye.
Bye. Thank
you very much. And good night to all my listeners in India, including myself. And good evening to all of you. Bye.
Bye-bye.
Thank you, Rohini and Melissa. Thank you so much.
Thank you. Bye-bye, Natanya.
Bye.
Thanks. Bye.